everyone. The lecture today is on quadratic functions, and this is the 9th lecture in our series, Mathematical Methods for Economics. I will be starting today's lecture by introducing the general form of quadratic functions, and there are two main aspects relating to quadratic functions that I will be focusing on in particular. The first is what we call the zeros of a quadratic function, which basically mathematically amounts to finding this to solving a quadratic equation. The second main aspect that we're going to focus on is the coordinates of the maximum or the minimum point of a quadratic function, which we'll see in a bit is graphically represented by a parabola. As always, we'll also be going over some practice problems, and I'll also bring in an example from economics for quadratic functions if we have time left in the end. But there is one important result that I would be talking about in this particular topic on quadratic functions, and this result is known as the Cauchy-Schwarz inequality. This is actually a very nice application of the work on quadratic functions, so do pay attention when I talk about the Cauchy-Schwarz inequality. Okay, then let's begin the lecture for today. If you take a look at the slide that I'm showing right now, a general quadratic function is of the form f of x equal to ax square plus bx plus c, where a, b and c are constants. In particular, there are two things that you should note here. The first is that the highest power of the variable x in this function is 2, right? And the second thing that you must notice here is that there is a restriction that we have imposed in this format, which is that a, the coefficient of x square, the constant a, is not equal to 0. This is because if a is equal to 0, you can see here, the function will become f of x equal to b times x plus c, which actually is a linear function. So this way we won't have a quadratic function, and that is why we are imposing the restriction that a is not equal to 0. But whether we are talking of linear functions or quadratic functions, cubic functions, or even higher order functions, all these are examples of polynomials. In fact, we can define a general polynomial of degree n as p of x equal to a subscript n, which I'll call as a sub n, times x to the power n, plus a sub n minus 1 times x to the power n minus 1, and so on till a2 times x square plus a1 times x plus a naught. So, for example, if n is equal to 1, this polynomial p of x will become a1 times x plus a naught, which we can see is a linear function. So, a linear function will be a polynomial of degree 1. Similarly, a quadratic function, which is the topic for discussion today, that is a polynomial of degree 2, because if I put n equal to 2 here in this general polynomial, we get p of x is equal to a2 times x square plus a1 times x plus a naught, and that is a quadratic function. Similarly, a cubic function is a polynomial of degree 3 and so forth. Now, a quadratic function is graphically represented by a parabola. It could be represented by a U-shaped parabola, and you can see here that this function, it first decreases. Please see where my cursor, how my cursor is moving. This function first decreases to some minimum point and then increases. Alternatively, the function could also be represented by an inverted U-shaped parabola, which opens downwards. So here the function, you can see, increases up to some maximum point and then decreases. In particular, here we are talking of parabolas which have a vertical axis of symmetry. The axis of symmetry is like the red line here. If you see this red line on the parabola that is opening upwards, the parabola on the left here, This is a line which divides the graph of this function into two identical halves. In fact, if I were to just fold this graph along this line, along this axis of symmetry, the two parts of the graph would exactly overlap with each other. Similarly, the axis of symmetry here is, for this second graph, is nothing but the y-axis. So these two kinds of parabolas are those which represent quadratic functions, either a parabola, a U-shaped parabola that opens upwards, or an inverted U-shaped parabola that opens downwards. Now you may be thinking that graphically parabolas could also be parabolas where the axis of symmetry is horizontal. For example, in the case here where the parabola opens to the right, or in this case, this bottom graph here where the parabola opens to the left. So the question is, why aren't these considered as quadratic functions? So if you notice here, for both these graphs, if you were to draw a vertical line through these, through any one of these graphs, these parabolas would fail the vertical line test for a function. So these parabolas don't even represent, they don't even define a function, leave alone quadratic functions. So we're not going to be considering parabolas where the axis of symmetry is horizontal as quadratic functions. Now, before I get into the details of quadratic functions, I'm going to talk a little bit about an age-old trick which is used in mathematics, and this method is known as completing the square. This is a method which you could, once I elaborate on it, you could use this to solve quadratic equations, or you could use this for any kind of proof or anywhere where this kind of a method comes in handy. Now, this is a process, this process of completing the square. It is a process which is used for expressions of the form. Please take a look at this slide. Expressions of the form x square plus twice ax. The question now is, if we have an expression which looks like x square plus twice ax, can we turn this into a perfect square? So we all know that if you take a look at this expression here, we all know that x plus a, the whole square, is equal to x square plus 2ax plus a square. Now this expression on the right, x square plus 2ax plus a square, this is known as a complete square because I can write this as x plus a the whole square. Now look at the expression in question. Our expression in question is x square plus 2ax. The question now is, what can I do with this expression so that it mimics this expression here in equation number 1, this expression on the right hand side? Because if I can get my x square plus 2ax to look like the right hand side expression in equation 1, then I can turn this into a complete square. And you can see here, it's very obvious that the only term that is missing from our expression x square plus 2ax is a square. So what I'm going to do here is, in order to complete my square for x square plus 2ax, I'm going to add the term a square. Please see where my cursor is. I'm going to add the term a square to the expression x square plus 2ax. But then the point is, if I'm adding a square, then I also have to subtract a square to maintain the sanctity of the expression. Right. Now, if I write things in this way, you can see now that once I have x square plus 2ax plus a square, I can write this as x plus a the whole square minus a square, and there you go, we have transformed our expression x square plus 2ax into a perfect square. So our result here is x square plus 2ax is equal to x plus a the whole square minus a square. And here, instead of going through the long procedure, the kind of little proof that I just did on the previous slide, we can ask ourselves, is there a quick way or a trick to know what exactly I should put in the parentheses here? What is the value of a that I should put inside the brackets? And yes, the answer here is you can use this trick, which is that look at this coefficient of x. the coefficient of x is 2 times a. So all I have to do is I have to divide the coefficient of x by 2, and that will be the a that I will put inside the parenthesis here in the whole square term. And because effectively I'm adding an a square, I will be subtracting that term a square outside. So let's work through some examples to see if you have understood the process of completing the square. Let's just practice a little bit. Okay, the first expression is x square plus 6 times x. Also remember, when we have to follow the process of completing the square, we must try and make sure, we must make sure in fact that the coefficient of x square is 1. So let me just summarize. The first step is to collect all the terms that contain an x in the quadratic expression. So here it would be something like x square plus 2ax. Make sure the coefficient of x square is 1, and then you proceed. Okay, so our expression here is x square plus 6x. Look here, the coefficient of x is 6. So all I have to do is I have to divide this by 2, which gives me a 3. So therefore, I'm going to add and subtract the square of 3, which is 9, from this expression, x square plus 6x. So I get x square plus 6x plus 9 minus 9. And now I can write x square plus 6x plus 9 as x plus 3 the whole square minus 9. And I have that minus 9 term outside. Similarly, if I were to use a process of completing the square, if I were to complete the square for x square minus 4x, here note that the coefficient of x is minus 4, so half of that would be minus 2, and that's exactly the value that I'm going to put inside the parenthesis. So I'll get x minus 2 the whole square. But the point is, if I put minus 2 inside the parenthesis, for the complete square, I'm effectively adding a 4, so I also have to subtract the square of 2, which is 4, from this whole square. And a third example is where our expression here is minus 2 times x square minus 20x. Now remember, I told you, you should make the coefficient of x square 1. So here we will take minus 2 common, and we get minus 2 times x square plus 10x, where x square plus 10x is placed in brackets. Okay, so now we have to, our job is effectively to transform x square plus 10x into a whole square. And again, I'll look at the coefficient of x, which is 10, divided by 2, which gives me a 5. And then I'll add and subtract the square of 5 from this expression, which then gives me minus 2 times x plus 5 the whole square minus 25. And this in turn, if I just take the minus 2 inside and multiply it with the terms here, I'll get minus 2 times x plus 5 the whole square plus 50. So I hope this process of completing the square is clear to you with the help of these examples. And if you if you're still not clear, you can go back to this lecture on YouTube and just listen to this part again. And make sure that you know this this procedure of completing the square before we move on to the other parts of the discussion. Anyway, let's get back to our main discussion on quadratic functions. As I said in the beginning of the lecture, there are two main aspects relating to quadratic functions that we're going to be focusing on. And the first question here, we have these two questions of interest, and the first aspect that we're going to be focusing on is as follows. The question here is, for what values of x, if any, is f of x equal to 0? In other words, for what values of x, if any, is the function ax square plus bx plus c equal to 0? This effectively amounts to finding what are known as the zeros of the quadratic function. Now, what do we mean by the zeros of the quadratic function? Mathematically, when we talk of zeros of the quadratic function, this amounts to solving a quadratic equation, or this amounts to finding the roots, if any, or the solutions, if any, of a quadratic equation. Graphically, this would amount to finding the point or points where the graph of a quadratic function intersects the x-axis. Now, what do we mean by that? Because the point here is, so let's just understand this a little bit. We are trying to find the value or the values of x where f of x is equal to 0. Now, when I say f of x is equal to 0, that is the same thing as saying y is equal to 0. So, I want to look for those values of x where y is equal to 0. If I'm drawing a graph, now any such value of x where y is equal to 0 will lie on the x-axis. So, when I'm talking of the zeros of the quadratic function, graphically this amounts to finding the point or the points where the graph of the quadratic function or where the parabola intersects the x-axis. Okay, so let's get the math out of the way first before we look at the visuals. So, we are trying to find the solution of the equation ax square plus bx plus c. Here, we are going to be using the process of completing the square, which I just talked about a few minutes ago. And to do that, what we're going to do is we're going to take this coefficient of x square out and take this common because we want the coefficient of x square inside the brackets to be 1. So, we get a times x square plus b by ax plus c by a, and that has to be equal to 0. Now, if you remember, in the beginning I said that for a quadratic function, for us to have a valid quadratic function, we can't have a equal to 0. So, because a is not equal to 0, it must be the case that x square plus b by ax plus c by a is equal to 0. So, now if we put that equal to 0, we get x square plus b by a times x is equal to minus c by a. And now we are ready to use the process of completing the square, because if you notice, our left hand side expression in this equation, x square plus b by ax equal to minus c by a, is of the form that we just talked about when we when we follow the process of completing the square. Now, notice here that the coefficient of x is b by a. So, the half of 1/2 of b by a would be b by 2a. And what I'm going to do is I'm going to add and subtract the square of b by 2a from this expression, which actually amounts to adding the square of b by 2a to each side of the equation. And that then gives me x square plus b by ax plus b by 2a the whole square is equal to, so if I'm adding b by 2a the whole square on the left hand side, I also have to add it on the right hand side, and that then gives me on the right hand side minus c by a plus b by 2a the whole square. Okay, so now if you notice here, the left hand side can now be completed into, can now be written as a perfect square, which is x plus b by 2a the whole square is equal to minus c by a plus b square divided by 4a square. Right, now this expression in turn, I can manipulate the right hand side. If you notice here, if I take the LCM is going to be 4a square, and in the numerator I will get b square minus 4ac. So, my equation now becomes x plus b by 2a the whole square is equal to b square minus 4ac divided by 4a square. Remember, we were out here, we are trying to find the roots of the equation ax square plus bx plus c, and we have converted that equation into this form in order to solve our equation. Okay, so now we are in a position to solve this and get the values of x. If so I can now write x plus b by 2a equal to plus minus square root of b square minus 4ac divided by 2a, taking the square root on both sides. And in this way, I get the solution for x, which is what you all are familiar with as a solution, or solutions for the quadratic equation, which is x is equal to minus b by 2a plus minus square root of b square minus 4ac divided by 2a. Now, this formula is going to be valid, please note here, as long as b square minus 4ac is greater than or equal to 0, because this is something we did in one of the earlier lectures. If b square minus 4ac is negative, then then our quadratic equation will not have any real solutions, because we can't define the square root of a negative number over the real line. So these are the solutions. The solutions are given by this formula, x equal to minus b by 2a plus minus square root of b square minus 4ac divided by 2a, as long as your b square minus 4ac is greater than or equal to 0. And by the way, this expression b square minus 4ac is also known as the discriminant. Discriminant, I should have written it here. So this is spelled as D-I-S-C-R-I, discriminant, so M-I-N-A-N-T. Okay, so the point here is that we can have two possibilities here. If b square is greater than 4ac, if b square is strictly greater than 4ac, then our quadratic equation will have two distinct real roots, which would be given by minus b plus square root of the discriminant divided by 2a and minus b minus square root of the discriminant divided by 2a. But if b square is equal to 4ac, then both our solutions will boil down to the same number, and in that situation we say that we have a repeated root. We have the equation has one real root, and that is the case of a repeated root, because effectively the two solutions are one and the same. And again, I emphasize that this formula is, it gives us a solution or solutions as long as b square minus 4ac is greater than or equal to 0. Okay, let's also get a visual sense of things as far as the zeros of a quadratic function are concerned. So here on this slide, I have shown you three parabolas that open upwards, all of them open upwards. And there are three cases here. So the first one is b square minus 4ac is strictly greater than 0. The second one where b square is equal to 4ac, and the third parabola is the one that corresponds to b square is strictly less than 4ac. So what I'm trying to show here is that depending on the sign of b square minus 4ac, you can have a parabola that intersects the x-axis at exactly 2 points, or it just touches the x-axis. So let me do it one by one. If b square is strictly greater than 4ac, you have a parabola here that will intersect the x-axis at 2 points, namely x1 and x2, because here we have two real roots. If b square is equal to 4ac, then the parabola here will just touch it is just touching, you can see here, the x-axis, and because there is only one real root, that real root is then given by x1. So here you have a parabola which is literally just sitting on the x-axis at this point, x1. And finally, if b square is less than 4ac, then because we have no real roots, this is going to be a parabola which will lie above the x-axis everywhere. It is not going to intersect or touch the x-axis anywhere. Similarly, look at these three parabolas which open downwards. Again, if b square is strictly greater than 4ac, our quadratic equation will have two real roots, in which case the parabola will intersect the x-axis at 2 points, say x1 and x2. If b squared is equal to 4ac, then you can see here an inverted U-shaped parabola of this kind will just touch the x-axis at 1 point. And if b square is strictly less than 4ac, here we have no real roots, in which case the parabola lies below the x-axis and does not intersect the x-axis or touch the x-axis anywhere. So what we have seen here is that depending on the sign of b square minus 4ac, our parabola may or may not intersect the x-axis. The question here is, what about intersection with the y-axis? If I give you a parabola which is a quadratic function, will it intersect the y-axis, and if yes, where? So the point here is whether or not a parabola intersects the x-axis it is always a case that a parabola will that represents a quadratic function will intersect, it will always intersect the y-axis. And to see this, basically when you're talking of intersection with the y-axis, that means you're looking for the y-intercept. So to look at this, look here that our quadratic function is ax squared plus bx plus c. Right? So if I want the y-intercept, all I have to do is put x equal to 0. So basically the constant here, which is represented by c, that represents the y-intercept of a quadratic function. So a quadratic function will always intersect the y-axis. Now, this was as far as the first question of interest was concerned, which was related to the zeros of a quadratic function. Now we're going to talk about our second main aspect, the second area of focus for this topic, which is the coordinates of the maximum or minimum point for a quadratic function. And here, note that the maximum or minimum point, which I have represented here as P on the slide, this is nothing but the vertex of the parabolas that I have here, the vertex of the parabola. The vertex of a parabola is nothing but the point where the graph of the quadratic function intersects the axis of symmetry. So here, if you notice, this point P here on the graph on the left is the point where the graph in blue intersects the axis of symmetry. Similarly for the graph on the right, and this vertex in turn corresponds to the maximum point. So if I represent the point, the vertex as point P, the point P would be the maximum point for an inverted U-shaped parabola, and it would be the minimum point for a U-shaped parabola. Now let's get at the math. So our function is f of x is equal to ax squared plus bx plus c. Again, we will use the method of completing the square. So we will take a common, which then gives us in parentheses x squared plus b upon a times x, and then outside we're going to have a plus c, as the above expression is showing. Now, to convert x squared plus b by ax into a complete square, what am I going to do? I'll take the coefficient of x, which is b by a, divide this by 2, or take 1/2 of b by a, which is b by 2a, and add and subtract b squared by 4a square, which then gives me a times, once I complete the square, I get a times x plus b by 2a the whole square, but because effectively I've added b square upon 4a square, I've also subtracted here b square upon 4a square, and then I have my plus c outside the square brackets. Okay, so now what we're going to do is, let's take the a term inside, that gives us a times x plus b by 2a the whole square, minus b square upon 4a, because once I multiply a with b square upon 4a square, one of the a's will get cancelled, and I get b square upon 4a plus c. And then our function can be written as a times x plus b by 2a the whole square minus b square minus 4ac divided by 4a. Now this is an expression of a quadratic function, which is something that you might want to keep in mind, because this will now lead us to some very powerful results. So if our quadratic function is now written as f of x equal to a times x plus b by 2a the whole square minus b square minus 4ac divided by 4a, the claim here is, when the coefficient of x square in the quadratic function, which is a, when a is positive, the function attains its minimum at x equal to minus b by 2a. And when a is negative, when the constant a is negative, the quadratic function attains its maximum at x equal to minus b by 2a. So let's see how this works, and please pay attention here, because this is something very important. So we have, as I just mentioned, we've written our quadratic function as a times x plus b by 2a the whole square minus b square minus 4ac divided by 4a. So basically, if you just stare at this, at the way we have expressed a quadratic function, this f of x consists of two terms. One term is a times x plus b by 2a the whole square, and the second term is minus of b square minus 4ac by 4a. Now note here that as x varies in the function, then it is only the first term that is going to vary, because this variable x appears only in the first term. But if you look at the second term, that is a constant, that is independent of x. So for example, when I put x equal to minus b by 2a, I'm going to get minus of b square minus 4ac divided by 4a, and this is something which is independent of x, and let's call this value as s. That will just make things more convenient. But what I'm trying to emphasize is that as my x will vary, it's only this first term that is going to vary, because it's only the first term that contains an x. Right. Now, let's write, just for the sake of convenience, let us write our function f of x as s plus a times x plus b by 2a the whole square. So I'm basically writing this minus b square minus 4ac divided by 4a expression as s, and to this value I'm going to add a times x plus b by 2a the whole square. So it's just a different way of writing the same expression. Okay. So we have two cases here now. One where a is positive and the other where a is negative. Let us suppose first that a is positive. Now we know that when x is equal to minus b by 2a, then the value of the function is nothing but s, because once we put x equal to minus b by 2a, this term here will, where my cursor is, this second term will vanish and the value of the function is s. But suppose x is not equal to minus b by 2a. Let's suppose x is some value other than minus b by 2a. Then the function f of x will be given as that value s plus a times x plus b by 2a the whole square. Now because a is positive and x plus b by 2a the whole square is always going to be non-negative, here we have a situation, in particular x plus b by 2a the whole square will be positive because x is not minus b by 2a. So here we have a situation where we are adding some value to the value s. So this resultant expression s plus a times x plus b by 2a the whole square is always going to be strictly greater than s. So in this sense, s becomes the minimum value of the function s. Why? Because I'm adding something positive, because a is positive and x plus b by 2a the whole square is positive always. In this case, when x is not equal to minus b by 2a, so I'm always going to be adding something to the number s. So if I'm adding something to the number s, the minimum value of the function is always going to be s. And in this case, when a is positive, we say that the function attains its minimum at x equal to minus b by 2a, where the minimum value is f of minus b by 2a equal to minus of b square minus 4ac divided by 4a, because we're claiming that the minimum value is s, which is nothing but minus of b square minus 4ac divided by 4a. That minimum value, because it's achieved at x equal to minus b upon 2a, therefore x equal to minus b upon 2a is where the function attains its minimum. Now this can also be understood visually, as I was just saying, at x equal to minus b by 2a, I forgot to label the axes here, I apologize for that, but if x is equal to minus b by 2a, the value of the function is s, which is minus of b square minus 4ac divided by 4a, and the point here is whenever x is something other than minus b by 2a, so if you move to the left of minus b by 2a or to the right, then I'm always going to be adding something to the value s. So in that sense, my s is the minimum value. Minus of b square minus 4ac divided by 4a is the minimum value of the function. I hope that's clear to you. That's a very important result, so please take note of it. And now let's look at our second assumption. If we have that a is negative and x is something other than minus b by 2a, note here that our function will then become s plus a times x plus b by 2a the whole square. But now this resultant expression is always going to be less than s. Why is that? Because a is something negative, x plus b by 2a the whole square something positive. Now because a is something negative, you're always going to be subtracting something from the value s, right? So if you're always going to be subtracting something from the value s whenever x is not equal to minus b by 2a, s has to now be the maximum value of the function. So whenever a is negative, we say that the function has a maximum, and because the maximum value occurs at minus b by 2a, we say that the function achieves its maximum at x equal to minus b by 2a, with the maximum value being minus of b square minus 4ac divided by 4a. So this is how we summarize the entire discussion for the coordinates of the maximum or minimum point. Let me just read it out to you. If a is positive, the function ax square plus bx plus c has a minimum at the coordinates minus b by 2a, comma, minus of b square minus 4ac divided by 4a. If a is negative, the function f of x equal to ax square plus bx plus c has a maximum at minus b by 2a, comma, minus b square minus 4ac divided by 4a. Now actually this is a very powerful result, because here you have been able to find the maximum or minimum without getting into any kind of calculus. So if you've done a class on calculus, you would know that you would be calculating derivatives and finding the stationary point in order to get your max or min, and then you would be substituting back those values into the function to get your max or min values. But look here, this is something which is totally independent of that kind of a calculation. The point is, the moment you see a quadratic equation, quadratic function, which is ax square plus bx plus c in a general sense, the moment you see that a is positive, the coefficient of x squared is positive, that should automatically send a message, give you that message that this function is going to have a minimum. And where is it going to have its minimum? At minus b upon 2a. So you don't even have to get into derivatives, and in that sense this result is quite powerful. Okay, so based on that, based on what we've just talked about, let's just experiment a little bit with these a's and b's. So look here, we have four possibilities. The first one being where a is positive and b is greater than or equal to 0. So as we just mentioned, whenever a is positive, the function has a minimum. Now where does it have a minimum? It has a minimum at minus b upon 2a. So let me just back up. Because a function has a minimum, we're going to be graphically representing it as a parabola that opens upwards, because you can't have, an inverted U-shaped parabola is going to have a max. So that's why I've shown you parabolas here that all open upwards. And the minimum point is x equal to minus b upon 2a, which in this case, note, will be less than or equal to 0, because your a and b are both, a is strictly positive, b is greater than or equal to 0. So in that sense, minus b upon 2a is less than or equal to 0, which is to say that the minimum point will occur on the negative side of the x-axis. So in this case, that is what I've shown in all these graphs, in all these three graphs here in this panel. The minimum is occurring on the negative side of the x-axis. So if you see, the p is to the left of the origin. And also, depending on whether b square is greater than or equal to or less than 4ac, we'll have 2 real roots or 1 real root or no real roots, and in this sense you can try experimenting with different kinds of graphs. I'll leave this to you as an exercise. What will be the shape of the graph when a is positive but b is less than or equal to 0? Let me do another one. Let's suppose a is negative but b is greater than or equal to 0. Now, because a is negative, this means that the function has a max, which means that graphically it's going to be represented by an inverted U-shaped parabola that opens downward, and the max will be given by the maximum point will be at x equal to minus b upon 2a, which in this case you can see is greater than or equal to 0, because here a is negative, so that will make the whole term minus b upon 2a greater than or equal to 0, which is to say that the max will occur, it will happen on the positive side of the x-axis. A function will achieve its maximum value on the positive side of the x-axis, and depending on the sign of b square minus 4ac again, we'll have either two distinct roots as is shown in the graph labeled A in this panel, or you could have one root, one real root when b squared is equal to 4ac, or you would have the case where there are no real roots, in which case your maximum, which is represented by p, will be below the x-axis. So in this way you can experiment with different cases, and this is a fourth possibility where a is negative and b is less than or equal to 0. Okay, let's try some examples now to so as to check if you have understood this whole discussion on the coordinates of the maximum or minimum point. So this question says, complete the square for the following quadratic functions and then determine the max or min point of each. So the first quadratic function is x square plus 6x plus 2, and as a first step to completing the square, let's just isolate all the x terms. So that will be x square plus 6x, and that we'll place under parentheses. This, to complete the square, I will have to look here. If I look at the coefficient of x, that is 6. So the half of 6 is 3. So I'm going to add and subtract a 9 from this expression x squared plus 6x. And that then gives me x plus 3 the whole square. And once I take this minus 9 outside, so I get minus 9 plus 2, which is minus 7. So I get the function as x plus 3 the whole square minus 7. And here you can see, because a is positive, the function achieves its minimum at x equal to minus 3, and the minimum value is minus 7. So when x, you can see here, when x is equal to minus 3, the value of the function is minus 7. And if I take any value other than minus 3, you'll obviously be adding something by the amount x plus 3 the whole square to the value minus 7. So that means the value will only increase beyond minus 7. And in that sense, minus 7 is minimum value, and you can check here that minus 3 corresponds to your minus b by 2a. Okay, if our function is minus 1/3 x square minus 2 by 3x plus 8 by 3, this in turn can be written as minus 1 by 3 times x square plus 2x in parentheses plus 8 by 3. And because the 1/2 of 2 here would be 1, so I'll add and subtract a 1 here in parentheses so as to complete my square, which then gives me minus 1/3 times x square plus 2x plus 1. And let's take this minus 1 here where my cursor is out of the brackets, so I'll get plus 1 by 3, and then I obviously have my plus 8 by 3. Which then amounts to writing my function as minus 1/3 times x plus 1 the whole square plus 3. And this is an expression that attains its maximum value, which is 3 at x equal to minus 1. Our final function here is 4x square minus 8x plus 10, which in turn can be written as 4 times x square minus 2x, we take 4 common, plus 10, and then I'm going to add and subtract a 1 because the coefficient of x is minus 2, so I have to add and subtract the square of minus 1 here. The square of 1 is 1, so that then gives me 4 times x square minus 2x plus 1, and then once I multiply this minus 1 by 4, I get a minus 4 here outside the brackets plus 10. So this function is then written as 4 times x minus 1 the whole square plus 6, which is to say that the function achieves its minimum, which is 6 at x equal to 1. Okay, so let's now move on to our next example. This is actually getting at what we were talking about in the beginning of the lecture, which is the axis of symmetry, and we're going to show here that the axis of symmetry or our parabola, which represents a quadratic function, is symmetric about the line x equal to minus b by 2a. So it's actually that x equal to minus b by 2a line which acts as the axis of symmetry. But first of all, what do we mean by symmetry? So we say that the graph of a function is symmetric about the line x equal to p if f of p minus t is equal to f of p plus t. So this is to say that if p is your line, your axis of symmetry, if I go t units to the left of p or t units to the right of p, I'm going to get the same value for f, and that is what I mean by symmetry. If I were to just fold the graph, this line divides the graph into two identical halves, and if I just fold the graph along this line, I will get a situation where the two parts just overlap, they exactly overlap with each other. So we are going to show here that this line x equal to minus b by 2a is the axis of symmetry for our parabola. And to show that, we'll have to show that f of minus b by 2a minus t, because here our p is minus b by 2a, and that needs to be shown is equal to f of minus b by 2a plus t. Now note here, again we're going to be using this expression for f of x, this version of f of x which we just derived, which is a times x plus b by 2a the whole square minus of b square minus 4ac divided by 4a. And now if I put x equal to minus b by 2a minus t, because I want to look at f of p minus t, where p is minus b by 2a, so I get f of minus b by 2a minus t is equal to a times, so now instead of x here in this expression, I'm going to put minus b upon 2a minus t plus b by 2a the whole square minus, and then outside I have b square minus 4ac divided by 4a. Now you can see here this is nothing but a times t square, because this minus b by 2a will cancel out the b by 2a here. So I get that f of minus b upon 2a minus t is equal to a times t square minus b square minus 4ac divided by 4a. Similarly, let's now look at f of p plus t, where p is minus b upon 2a. So f of minus b upon 2a plus t is now going to be a times, again now instead of x, I'm going to substitute minus b upon 2a plus t plus b upon 2a the whole square minus of b square minus 4ac divided by 4a. And here again you can see that the b by 2a terms will get cancelled, and I'm going to be left with a times t square minus of b square minus 4ac divided by 4a, which we just saw is also the same as what we got for f of minus b upon 2a minus t. So from this calculation we conclude that minus b upon 2a is like the axis, it acts like the axis of symmetry. So that if I were to move t units to the left of this line or t units to the right, the value of my function is going to be exactly the same. Okay, now this is an interesting example which actually then leads us to our derivation of the Cauchy-Schwarz inequality. And this question asks us, under what restrictions on the parameters a, b and c is a function f of x equal to ax square plus bx plus c greater than or equal to 0 for all x? Now, to understand, before we get into the math of this, let's just try and get a visual sense of things here. If I want the function to be greater than or equal to 0, the value of the function to be greater than or equal to 0 for all values of x, that means a function should never lie below the x-axis. So visually, let me just back up and take you to one of the earlier slides, which would be slide, I think, 12 or 13. So suppose you look at these graphs. Now, this is a situation if you have two distinct roots, and clearly this graph is going to go below the x-axis, but this is not what we are asking. We want the graph to be greater than or equal to 0. We want the value of the function to be greater than or equal to 0 for all x. So clearly our solution has to look like either this graph or this graph. Similarly, if I were to look at these inverted U-shaped parabolas, not even one of these graphs would qualify to be part of our solution, because all these graphs have parts that go below parts, or they, in fact, in this third case, the graph entirely lies below the x-axis. Okay, so basically that was to give you a visual sense of things. Now let's just go through the math. We have two possibilities here. Either b square minus 4ac is positive, or the discriminant b square minus 4ac is less than or equal to 0. Now, if b square minus 4ac is positive, clearly this is a situation where our function f of x, where our equation f of x equal to 0 has two real roots. Now, if our graph has, if our equation has two real roots, this is clearly something which is not going to happen when f of x is always greater than or equal to 0 for all x, because if there are two real roots, there will always be some part of the graph which will lie below the x-axis. For some values of x, the value of the function would be negative. Now, if b square minus 4ac is less than or equal to 0, we can have two possibilities here. Either a is positive or a is negative. Now, if a is positive, note here in our expression for f of x, this modified version, if a is positive, this first term is going to be positive, and this second term will become, we have a times x plus b by 2a the whole square, minus of b square minus 4ac upon 4a. So this makes our function greater than or equal to 0, because b square minus 4ac is less than or equal to 0. So the second term will become greater than or equal to 0. But if a is negative, then in that case the first term is negative, and the second term would then become negative as well, because b square minus 4ac is less than or equal to 0, and your a is negative, so that would then cancel out the effect. So the ratio here is positive and you have a negative sign in front, so the entire sum is going to be less than or equal to 0. F of x is going to be less than or equal to 0. So our solution here is that when we have to place restrictions, we should have that a is positive and b square minus 4ac is less than or equal to 0, with no restrictions on b and c in particular, but b square minus 4ac has to be less than or equal to 0, and yes, a definitely has to be positive. And this is exactly what I was talking about in the pictures that I was showing you earlier. Let me just go back to that slide again, graph 12. So these are the two pictures where you see b square minus 4ac is less than or equal to 0, and because these are parabolas that open upwards, we have a as positive. So that exactly is our solution. Okay, now the last thing that we're going to do for this lecture is what is the derivation of the Cauchy-Schwarz inequality. Now let's suppose a1 through an and b1 through bn are arbitrary real numbers. So the Cauchy-Schwarz inequality says that a1 times b1 plus a2 times b2 and so on till an times bn is less than or equal to a1 square plus a2 square and so on till an square times b1 square plus b2 square and so on till bn square. To derive this inequality, which is actually a very important inequality, let us define a function f of x which is equal to a1 times x plus b1 the whole square plus a2 times x plus b2 the whole square and so on till a sub n times x plus b sub n the whole square. Now note here, because this is a sum of whole squares, f of x is always going to be greater than or equal to 0 for all x. And let us also do this exercise where we collect all the x square terms. Let's just open up the brackets for f of x. Let's collect all the x square terms, the x terms and the constants. So we get f of x is equal to a1 square plus a2 square and so on till an square times x square plus twice a1 b1 plus a2 b2 and so on till an bn times x plus b1 square plus b2 square and so on till bn square. Now, this in turn can be written as a quadratic function which is given by capital A times x square plus capital B times x plus capital C, where capital A is a1 square plus a2 square and so on till an square, capital B is the coefficient of x and C is b1 square plus b2 square and so on till bn square. So we have reduced our function f of x to a quadratic function of the form ax square plus bx plus c. Also, as we just discussed in the previous example, because f of x is non-negative everywhere for all x, the function cannot lie below the x-axis, we must have that the discriminant is less than or equal to 0. This is exactly what we discussed in the previous question. Now, what does this mean? If I put b square minus 4ac less than or equal to 0, now what is my b square? B square is 4 times a1 b1 plus a2 b2 and so on till an bn. Minus 4ac would be minus 4 times a1 square through an square times b1 square through bn square, and that has to be less than or equal to 0. Then you just have to manipulate the terms around and the 4's will get cancelled, and there you are. You are now able to get what we call the Cauchy-Schwarz inequality. It looks like we have run out of time for today's lecture. I would have liked to cover an application from economics to see how quadratic functions are used in economics. In particular, I wanted to go through a profit maximization problem, but I guess we'll have to leave that. We'll just take it forward to the next lecture. In the next lecture, I'll cover this application, plus I will also talk about the shifting of graphs and cubic functions as well. So that'll be the plan of action for the next lecture. Anyway, thanks for tuning in to this lecture for today, and take care. Bye-bye.